Before you do that, the last speaker today is my colleague Robbie Bickerton, also from University of Edinburgh. So Dr. Bickerton was employed more recently, and he and I have been working on how to assess proof, because that's the heart of our discipline for mathematics. Now, I think we're a long way from assessing free-form proof, right? I mean, I've been trying to establish links with the automatic theorem proving community and all the rest of it, but it's just a long way away. And what Dr. Bickerton is going to talk about next is our attempts to automatically assess proof and understanding of proof with Stack. So Robbie, over to you.
Thank you, Chris. Let me share my screen. There we go. So I think I'm going to leave this in this mode rather than presentation mode, because for some reason my mouse keeps going missing every time I put it in presentation mode. So, as Chris said, we've been looking into what we can do with regards to assessing proof in Stack. So the way I thought this session would work would be me talking at you all for about 20 minutes, half an hour, and then I'd maybe show you an example of what one of our proof comprehension exercises looks like in Stack. So I've structured this talk in the sense of each slide in theory should answer some of the most common questions I get about this topic, and I will pause for questions if there's anything that I haven't addressed. So, why do we want to assess proof online? Well, as Chris said, proof is essential to mathematics. It's something that maths is built upon, and it's something that we want all of our undergraduate students to be able to engage with and to understand. So why do we want to do this online? Well, many students traditionally are taught proof in the form of lectures where they are given a definition, then a theorem, then they are taken through a proof. And they are expected to listen to their lecturer read through this proof and then at some point reproduce it, whether that be in an assignment or in an exam. Now, the issue with just listening to a proof being proved or just reading through a proof is that these aren't necessarily active engagement. They aren't necessarily engaging with the proof. So our aim was to use online assessment and online tasks within Stack to try and get the students to engage with individual proofs more. And this allowed us to have a greater scope for proof tasks outside of just reading proofs or writing proofs. And of course, more importantly, if this doesn't have you convinced that this is a worthwhile thing, after COVID-19, unfortunately, this kind of thing is pretty much a necessity as more and more things are going to have to be pushed online. Now, as Chris said, there are some limitations with what we can do. The biggest one being that we can't automatically assess a free-form argument. So we can't get students to upload a proof of the Riemann hypothesis and get that automatically marked. So we have to be slightly more supple. So what we've done is to use a variety of comprehension tasks to try and assess whether students understand proofs, rather than getting them to provide a full argument. But this leads us into a slight problem, because what does it mean for a student to understand a proof? And I've spoken to a lot of mathematicians and a lot of mathematics educators, and no one can really seem to agree on the answer to this question. So for example, do we think a student has understood a proof if they are able to reproduce it fully and correctly from a lecture that they've been to or from a book? Okay, but what happens if that student has just happened to memorize the proof? Does that mean they've necessarily understood it? I don't know. And I don't necessarily have an answer to this question. And it's just something that we have to bear in mind when we're writing these online questions, because we need to be aware of what we actually want to test the student about with regards to the proof. The final issue is one of a sense of technical expertise. So my background isn't necessarily as a stack expert. I was a pure mathematician, and I only started writing stack questions in the last year. So hopefully this session can kind of mitigate the lack of technical knowledge somewhat. But I've found that proof questions aren't necessarily the most complicated ones to write in stack. Hopefully this will become clear over the rest of my talk. So how do we solve these issues that I've mentioned? Well, I've already talked about proof comprehension exercises, and these can take a variety of forms, and in fact, we've used several different types. So these can involve things like asking students to provide the structure of a proof. So is a proof a contradiction? Is it an if and only if proof? Questions along that line. It can also involve asking students to pick out specific lines from a proof. But there are also a couple of other things that we can do. So I mentioned proof fading here. George talked about faded worked examples in his talk. We can do something similar for proofs. So for example, we could provide the structure of an induction proof, but then leave the lines of calculation blank for the student to provide. We can then automatically assess the calculations that the students are doing. And finally, there is an option in Stack for the implementation of human marked questions. So there is a note answer type where students can type in their answers, but they have to be marked by a human. So it is possible to do within Stack. So the next part of my talk is going to be about specifically a Stack question that I wrote last year about a proof for one of our courses. It's first year introduction to proofs course here at Edinburgh. I should say that everything I am going to speak about in these slides and in my talk today, they're all available in a paper that Chris and I wrote that's currently available on the archive. And I put a link to that in the Moodle site for this workshop. And I will reference it again at the end of my slides. So before I move on, maybe I should stop for questions briefly. My chat seems to have disappeared. So if anyone can tell me if there's any questions coming up.
I don't think there's been any specifically for you, Robbie. I think you're okay. I'll keep an eye out.
Thank you. Excellent. So I will push on. So this is the general process that I've been going through every time I want to take a proof, either from a course textbook or from course notes, and to turn it into a series of Stack comprehension questions. So the first task is, how do I select a suitable proof? What proofs do I need? And there's actually quite a lot that goes into this selection of appropriate proofs. But we are essentially being driven by a practical need. So most often the reason that I would choose a proof is because a course leader would want to assess that proof. So it somewhat mitigates the choice that you have. But really it comes down to a teaching decision in your courses. What do you want to assess? What proofs do you think are important? The next step was to break down any given proof, essentially line by line. So the reason that I do this will become more apparent when I talk about putting this in Stack. But at this stage, this was just to help me as a potential question author to understand the different elements that were going into making up a proof. And again, this becomes a matter of instinct or mathematical and educational expertise to identify what we mean by the key elements of each proof. So for example, in the famous proof that there are infinitely many primes, this relies on the creation of the integer n, which is a product of all the previous primes plus 1. That could be a key element of that proof, because if a student can remember that they can do that, they're halfway there to proving the theorem. So in order to emphasize that, we may then want to write a question about this element of that proof. So after a while, it became apparent that there was a systematic way in which I could be doing this process. And this culminated in Chris and I writing this proof baseline checklist. And again, this is in our paper for further information. I won't go through all of this here, but essentially this checklist is picking out all of the different parts of a proof. And the idea is that as a mathematics educator, we can then create questions that can be marked in stack that test each different aspect of the proof. So for example, point 2 we have here, describe the overall modular recursive structure. Well, by this was just what I was speaking about earlier. So in other words, we can, pretty much every proof has a structure that, or at least the proofs that our students are going to be meeting. So we can 90% of the time ask them, what is that structure? What is happening in that proof? This checklist isn't designed to be used in order, and it's not the case that every item is going to apply to every type of proof. So not everything is going to be suitable. And again, it comes down to a teaching decision about what you want to assess within the checklist. So for example, if we have for an if-then proof in step 7, is the converse true or false? We may not be in the situation to ask this question. So we don't have to use all of these items. So in order to make this a little bit more clear, I'm going to take you through an example of a question that I wrote. And this was the theorem that we selected. And this appeared, as I said, in a first year introduction to proof course at Edinburgh. And theorem is, if we have a bounded increasing sequence, then the limit exists. And this is the proof that is taken verbatim from our course textbook. So this is the paragraph of the proof that the students will see in a textbook. So, as I said, the first thing to do was to break down the proof line by line and then to number those lines. So why do I want to number those lines? Well, this is a practical concern with regards to stack. So because we can't assess a free-form argument, we need a way in stack that we can refer to different lines of a proof. By numbering them, it means that if we ask a student to provide a line, they can just enter the number of that line, and then we can assess that automatically. I also found that it served a useful secondary purpose in that it helped to identify what was actually happening at each stage of a proof. So I found that specifically with proofs that I've become very familiar with, or very famous proofs, there were things that I would take for granted when I was reading them, whereas actually when I delved into them a bit more, there was possibly some subtleties I would miss on the first time around. The next step was to apply our checklist. So again, you don't need to remember specifically what these numbers are at this point, but just again to note that I didn't use every item of the checklist. So for example, 7 and 8 didn't seem appropriate for this question. Now, the advantage of the proof that we chose here is that it has several definitions at play. The idea of an increasing sequence, the idea of a bounded sequence, and the idea of convergence. So it would be possible to create examples or to ask students for examples of each possible combination of these ideas. So for example, in the table here, we could ask the student to provide an example of an increasing sequence that's bounded and convergent. So in other words, we would be asking the students to provide an example that satisfies our theorem. But then we can use these combinations in a systematic way. So can a student provide an example of an increasing sequence that's bounded, but that isn't convergent? Well, this would be a counterexample to the theorem that we've just proved, but do the students understand this? So we could ask something about that. So the third line, can we have an increasing sequence that isn't bounded, that's convergent? Well, this would be a counterexample to a different theorem. So this would be testing students' slightly wider knowledge related to these ideas. So As I said, in a systematic way, it doesn't take long to come up with several questions that ask students to provide several examples. So how many do we have here? We have, I think, 8 different combinations. We could ask students to provide 8 different examples in theory. Can I see an example? Yes, yes, that's the point of the rest of my talk. So my finished question in stack looks like this. So we have the proposition and the proof at the top of the page formatted in a separate box. George talked earlier about the div tags that we just implemented in stack in order to create proof environments. And again, these are to be found within the assessing proof stack docs. And as you can see, we have the proof that's numbered lines, and then we have 6 questions that we ask the students. So in question A, we're asking where the completeness axiom is used within the proof. So the answer to this is actually step 2. But if you think back to the initial proof from the textbook, this was actually explicitly stated. So what we've done here is to remove the explicit reference to the completeness axiom in the proof the student sees in order that we can ask them to provide that. Parts B and C are to do with students picking out the correct lines of the proof, so in this case, we want to know where the idea that of a bounded sequence is first used and where an increasing sequence is used. Parts D and E are simple multiple choice questions that are asking the students to pick out the correct definitions of boundedness and convergence. And part F is to find some form of example. So we want the upper bound for the sequence sin of n plus 7. So as I said, this was an early question that I wrote, and I think that there are some ways that we could improve this. And there are some issues that at the moment we don't necessarily have the tools to get around. So what do I mean? Well, firstly, parts B and C are asking the students for boundedness and increasing sequence, as I said, but the way that I've written the proof above, I actually use the words bounded and increasing. So for example, the answer to C is line 5, but in line 5, I specifically say as the sequence is increasing. So in other words, a student who doesn't necessarily understand the proof could game the system and still get a correct answer. The second issue I can think of is that part F isn't necessarily to do with comprehension about this given proof. So maybe I don't need this part. And finally, as I said earlier, I removed the explicit reference to the completeness axiom to ask for it. But is this not slightly counterintuitive? Because I'm making a proof more complicated to read, but I'm still trying to teach students how to understand it. So I'm not saying that I have the answers to all of these questions. I'm just saying these are some of the issues that we are facing when we are trying to come up with these comprehension exercises. So perhaps for the sake of my credibility, I'll move on to my next slide. So these are a couple of examples of other forms of comprehension that we have managed to successfully implement. So if I begin on the right, I spoke about the idea of fading a proof, and this is exactly an example of this. So this is an induction question, and we're asked to prove that the sum of the first n of natural numbers is equal to n squared. Here, the students are provided with the general structure of the proof, but they are asked to give us the statement Pn. Then these drop-downs are true or false questions, and then they are asked to do the suitable calculation. So in this case, it again becomes a decision of how much of the induction structure you want to give to your students. So here, this one is quite heavily scaffolded, but as George mentioned earlier, we could roll that back and ask the students to provide more, depending on where this question is appearing, depending on context. On the other side of the slide, we have something else that we tried, which was to critique a given proof. So here we have an incorrect proof that -1 is equal to 1, and the student is asked to find which line this proof goes wrong. And the more interesting thing about this question is this second part here. We ask them, why is this line incorrect? Well, this is an example precisely of a notes answer where we're asking students to type in free form what their reasoning is behind their answer. So this would have to be marked by a human. And in fact, I believe that when we deployed this question, this wasn't for any marks, but this helped us to understand when students were going wrong, what was their reasoning behind going wrong? Why were they going wrong? And overall, for the questions that we've managed to deploy, we've found that there is actually less of a floor ceiling effect than we would expect. These tasks we're giving students are not necessarily straightforward to them. Whether this is because they aren't asked this in other courses or it's a novelty factor of the things that they've come across, we're not sure. But these things are not, it's not like students are doing these quizzes and then immediately getting 100%. So there seems like there is some value in doing these questions. So what about the future? Well, in the short term, I'm involved in trying to apply these ideas to other topics. So currently I'm writing some questions to do with linear algebra proofs. Secondly, we need to look into fixing some of the issues that I mentioned. So specifically, even though we have the ability to number lines of a proof, we found that it's still quite difficult to unambiguously refer to specific lines within an argument. There are still issues coming up with that despite the numbering. Thirdly, Chris and I would have liked to do some sort of evaluation of these questions, but we were interrupted by the COVID outbreak, and we both felt it would be more useful to put these ideas out in the open so that people could have or get some idea about how they might implement similar things into your own courses. And finally, this is a question that I don't know the answer to, and I would like to investigate. How far can we push these ideas? I don't think that we've reached the limit of what we're doing with this yet. I think we've made a decent start, but it'll be interesting to see just how far we can go with regards to these automatically marked comprehension tasks. So finally, where can I go for extra information? Well, as I've said, everything that I've talked about is available in Chris and my paper, which is available on the archive. And as I said, there's a link on the Stack Oodle site. For help formatting proof comprehension questions in stacks, there is the Stack Docs page. It's very useful. For further information, I would suggest looking at the references we have in our paper. And we will monitor the forum here for the rest of the day. But if you have any questions beyond that, feel free to email me if you're interested. So that was where I was going to end my talk before I show an example. So maybe I will stop here for some questions.
I don't see any questions right now, but Tim had an interesting comment about an idea for grading sort of why is this line incorrect style questions. I don't know, Tim, if you want to elaborate yourself.
Remember to unmute. It was really actually a bit of spam that we've got a question type that can grade short free text responses. If you want another complicated question type for your Moodle site, it exists. Just thought I'd let people know that.
Okay, thank you. Anything else?
There was also the question, does this from Alex?
Tim?
Yes.
Could I ask you, thank you for raising that. I mean, the work that you've done with the pattern match question type is really impressive. Could I trouble you to post something in the forum about that so people can really follow it up?
Yes.
Thank you.
I think Heather has a question. Heather, do you want to read it out yourself?
Hi, yeah, I was just looking at the proof questions because I'm going to do some for next term. And of course, maths, natural numbers don't include zero, but in computer science they do. And I'll match the textbook, so I'll have to have zero. So I'll have to talk to Robbie, I think, about that.
Is that a spiritual issue about the definition of the natural numbers or a practical issue about stack, Heather?
It will be a practical issue in that probably you might have to have two versions of the same question, one that's more computer science, you know, if you were doing a natural number proof, which I noticed Robbie was doing.
Yeah, I have to say,
issue.
in other natural numbers proof questions that I've done, I've copped out and just defined them as whatever I want them to be. I've said let n 1 onwards, so it's unambiguous.
Okay.
Well, we've accommodated the physicist with j for the square root of -1, so I'm sure we can accommodate the computer scientist with 0 as well at some point. We'll fix that.
Okay, so just raising it to think about.
Thank you. So I thought just to end my section, it might be quite useful just to have a look at what the question authoring page looks like for the proof comprehension question that I did. So I thought I would share my screen and just quickly go through that. So let me reshare this. So can everyone see my two stack windows that are open? Yeah. Excellent. So this is just the Moodle page for this workshop. So I'm just going to the question bank and I've put the proof comprehension question in the question bank to have a look at. And on the right is just the preview of what it looks like in Stack. So I just thought I'd quickly go through this. Even quicker because George helpfully explained exactly how to do multiple choice questions in Stack. So I don't need to explain any of this other than that in my question variables here are just the answers to each part of my question. And these long lists are just the multiple choice options coming up.
Could I interrupt actually? So I was noticing a question in the chat, which seems that someone else answered basically, but I was interested in your take on it, which is why use Stack for this if it's a multiple choice question? Do you think there's an advantage here?
Not necessarily. So for us, it was a matter of formatting almost at this point. So we want, on a practical level, we want the student to be able to see the proof as they do the comprehension questions about it. That was the main reason. But in theory, you certainly could use the Moodle type multiple choice question, for example.
Yeah, so this is keeping it sort of compact, I suppose. It's got
that's exactly it, yeah.
as one item. Yeah. So
pretty much everything we did was kind of from a practical point of view. So it was, as we kind of thought, for students, for the experience the students have when doing this question, we don't want them having to click back and forth between two different pages, essentially. So yeah, just to quickly go through the question text. These are the div classes that are explained in the Stack docs. So the proof class is precisely the thing that's setting my proof in the pale blue box. Proof line is the line of the proof. The numbers just helps with proof numbering, and then we can add in proof steps, which are the actual argument in the proof. And then we have the end of the proof itself, and then the questions that we're asking our students. And these, again, I would suggest that these aren't necessarily the most complicated questions to input in Stack, but I thought it would be useful to have at least an example of how we've laid this out. And finally, we have just our worked solution for each part of the question. So I don't think there's anything else to see really, because the potential response trees are pretty simple. So for example, we only need to test in part A whether 2 is the correct answer, so it's not too difficult to write the response trees. So let me...
Can I jump in here?
Yeah.
You've shown us one question, but what struck me about this whole endeavour is quite how many different questions you end up asking on one single proof. So here we've got one of your more complicated single questions, but we have a little bit of time. So could you show colleagues the sequence that you wrote for the Cauchy-Schwarz inequality?
Yes.
Because I think that has got a Moodle multiple choice where we've actually got a sequence of questions about one proof. So we are using the Moodle multiple choice where it makes sense.
Yes.
So perhaps you could just talk through, colleagues, this whole sequence where this is just more than one stat question, isn't it?
Yeah, so this is what I've been writing for Introduction to Linear Algebra for next term. So we're attempting to write a proof comprehension quiz per week about one of the most important proofs that students will meet from the book in that week. So in week 2, for example, we thought it would be good to go through some questions regarding Cauchy-Schwarz inequality. So we've laid these out in a, as Chris said, in a slightly different manner. So this, I will preview the full quiz. So maybe I can get rid of this window and maximize that. So here what we've done is we've written 7 questions that are all in some sense related to either directly to the proof of Cauchy-Schwarz inequality or related to techniques that are used in the proof of the Cauchy-Schwarz inequality. So question 1, for example, is just to give an example where it holds. Question 2 is a proof comprehension question where we faded the steps of the calculations. So we expect students to be able to expand the left-hand side, expand the right-hand side, and then perform the rest of the calculations to get the proof.
Robbie, can I just interrupt you quickly?
Yes.
Would you be able to zoom in a little bit? I think some people are having a difficulty seeing the text.
My apologies. Is that better?
I think that looks good to me, yeah.
Excellent.
Thank you.
No problem. So I think the reason that I didn't was because I'm wedded to the nicer formatting when you look at it further zoomed out. But yeah, so question 3 would be an example of a Moodle multiple choice question. So here we've decided to, instead of having the proof and the question about the proof as one stat question, we've split up everything into separate questions. So this is a Moodle multiple choice. And yeah, we expect students to pick out the times when equality would hold. So if I flip to the next page of the quiz, we actually have another multiple choice question. This is again just testing whether students understand the definition of the projection. And once again, we expect students to pick out the correct properties to do with this. Then they're given an example of where they have to find the given projection. And then finally, they're asked to implement this into a second proof of the Cauchy-Schwarz inequality. So, and again, in this case, we have a couple of questions that ask students to pick out the correct lines where certain properties are used. And finally, we're trying to end most weeks with a free text response question. So this is again something I have to type here. We expect students to provide some form of reasoning in this box that has to be assessed by a human. And actually there's a box that comes up reminding me of that fact, that this isn't going to be assessed by Stack. So in this case, we're asking students to debate or to consider why one of the proofs of the Cauchy-Schwarz that they've met may be better or worse than one of the others. So the hope with that is just to try and get them to think about it at a slightly different level. And this is the formatting that we are using for all of our quizzes in ILA.
So with question 1 there, Robbie, Let's just look at question 1 a bit more slowly. How does that fit with your proof baseline checklist?
So what we're asking the students to do, we're asking them to show an example of the Cauchy-Schwarz inequality. Part of the checklist is to provide specific examples. I think it was step 8 off the top of my head. So this question was precisely created by me writing out our checklist and then writing a question for each point in that checklist, or each point that was relevant.
Right, and that's also about what the theorem's about, isn't it? So it's about dot products. Do the students, this is week 2 of their university, so do they really remembered what a dot product is, and about norms as well. So just setting the scene before the proof a little bit, isn't it?
Exactly. Precisely.
And then you do that in question 5 again when the next proof comes on to projections.
Exactly. So essentially the question about finding an example of a projection, so question 5 and question 1 are providing the same kind of test. We're asking them to provide some example before they go on to the proof. And then they're asked to use the definition of a projection in the second proof in question 6.
Okay, so questions, colleagues, I think.
I think Mark had a question for Robbie earlier. Mark, if you'd like to ask it.
Oh, hi, Robbie. Thank you. That was a really inspiring talk. It's sort of a comment and a question. So when I'm thinking about courses I've lectured, say in my combinatorics course, I used to have a lot of fun giving bijective proofs of fairly simple binomial identities. And it occurred to me that you can sort of run these proofs just by putting explicit numbers in and getting explicit bijections between sets. And I think one thing Stack might be rather good at would be you could ask students, make an instance of this proof and then write down images or domains for these various maps. And there's some syntax there. So although it's not so deep, we would be leveraging the Stack computer algebra capabilities. So I was just wondering if you had any thoughts on this idea of turning proofs into examples.
So I think that's an excellent suggestion. Actually, this is something that we do address in our paper, and it's the final part of our checklist is precisely this idea. So I think there's a slight disconnect between what we as mathematicians do when we read a proof and what students do when we read a proof, or what we think they do. And I think we don't necessarily ask them a lot of times to give an example of things like this, precisely as you said. So I think it's a very worthwhile. I think it's a worthwhile thing to be doing. And as I say, I think this is part of the final point in our checklist, is to look at questions like this. So
can you put that slide up again easily? Is it possible to put that?
Yeah. Give me a second. There we go. So point 8, can you follow through the proof steps with a specific example? This is precisely that kind of situation. So I haven't showed them here, but we do have similar questions along those lines. I think it's an excellent idea.
Okay, any other questions?
I don't see any specific questions for Robbie, but we do have some more general questions we didn't have time for in the earlier talks if we want to move on to general Q&A.
I can stop sharing.
Firstly, thank you, Robbie, for presenting that. Thank you very much. Let's do that. Let's move on to general Q&A.